Okay, so from the previous lecture, we have understood how these possible polynomials, when multiplied, then it will generate x to the power 7 plus 1. Okay, so this is the non-zero elements of GF8. So when these non-zero elements are multiplied, this will generate x to the power 7 plus 1, which is satisfying this formula from the PDF book. We have shown you from the definition at the appendix B, that part. Okay, that definition was what? A property of the irreducible polynomials over the binary field GF2 of degree m is that they are the factors of polynomials x to the power 2 to the power m minus 1 plus 1. Okay, so here we have considered the generator polynomial as 1 plus x cubed. So highest degree is 3. So this is the factor. That means the generator, our generator polynomial is a factor of x to the power 7 plus 1. Right? So our generator polynomial x plus 1 plus x cubed is a factor of x to the power 7 plus 1. One of the factor, right? So we can say that generator polynomial can be generated by multiplying all of its factors, right? Because x to the power 7 plus 1 is formed by multiplying 1 plus x cubed, 1 plus x plus x, 1 plus x square plus x cubed, and 1 plus x. So those are the factors of x to the power 7 plus 1. So here we have considered generator polynomial as 1 plus x cubed, which is one of the polynomial of one of the factor polynomial of x to the power 7 plus 1. So we can say, if we consider the generator polynomial as x to the power 7 plus 1, then we can say that this x to the power 7 plus 1, or our generator polynomial x to the power 7 plus 1, is the multiplication of the factors of its factor polynomial. That is exactly written here, that the generator polynomials of the cyclic codes are the product of the irreducible polynomials, and so they are the product of minimal polynomials. Okay, so therefore we can look at cyclic codes. Therefore we can look at cyclic codes in terms of roots of the generator polynomials. That means we have already discussed several times that what is the concept of considering the roots as our syndrome technique. That means how we can use the roots of the generator polynomials in case of syndrome technique. How we can use the roots of the generator polynomials, or how much this is important, the significance of the root in case of correcting and detecting the received error of the code bit. That means received code bit error. Okay. So that is basically written. Therefore, we can look at the cyclic codes in terms of roots of generator polynomials Gx. Okay. Okay. So this was basically for the GF8. That means 2 to the power 3, where the 3 was the highest degree of the polynomial. Okay. So now, though it is not in your syllabus, but I'm just trying to show you that this is also applicable for GF16. That means 2 to the power 4, where 4 is the highest degree. So the equation is x to the power 4 plus x plus 1. So for this case, we have to again derive this polynomials in alpha. And these are the corresponding vectors. That means 4-bit representation. So you can see that as same as the previous way, this is the roots. This is the all possible polynomials when considering the highest degree as 4. So this is x, x plus 1, and these are the corresponding roots of these polynomial equations. Okay, this is not included in your syllabus, GF16. I think rather we can say that this is not needed to uh, discuss about minimal polynomial. Okay, so our topic is minimal polynomials. So minimal polynomial equation we have understood. Now we will go back to our book and we will see that how this minimal polynomials are useful for error detecting. Okay, so there are some other purposes. So we will go to the BCH code chapter. That was 97. Okay. So here, so these are basically, we have already discussed that how alpha, alpha square and alpha to the power 4 has become the roots of the generator polynomial equation. And you can say that here it is written that in order to correct an error pattern containing two errors. Okay, so first of all, go to this para where it is. Okay, so this clarifies or verifies that alpha square is the root of generator polynomials of G1x and having code 7,4. Okay, by substituting all these elements by the extended field, it is possible to identify that alpha to the power 4 is the third root of the generator polynomial, that is G1x. And and also to state that 1 alpha cube, alpha to the power 5, alpha to the power 6, okay, are not roots of that polynomial. That means we have considered here the generator polynomial as 1 plus x cube. So, and also we have seen that the roots of 1 plus x cube are alpha, alpha square and alpha to the power 4. But from that table, when ultimately we are dealing with GF2 to the power 3, that means degree of 3. So another possible polynomial is x cube plus x square plus 1, whose roots are basically 1 plus alpha cube plus alpha to the power 5 and alpha to the power 6. We have seen from the table. Okay, so here for this x cube plus x plus 1, we can write in this way, like these are the roots, that is alpha, alpha square and alpha to the power 4, considering the polynomial equation as 1 plus x cube. So it may be written, it can be written as x plus alpha square and x plus alpha 4. This is a generalization of the polynomial equation. And you can say that this is the relation between the roots and the polynomial equation. So this is the thing. Okay, now the thing is that by substituting here, just see, very important, that by substituting in the expression for a received polynomials, okay, when we are substituting the roots, the known roots of the generated code, because we already know that what are the roots of the generated code, which is equal to the root of the generator polynomial equation. Okay, so we also know the root of the generator code. Now we don't know the roots of the received code. Okay, so this is the technique to see whether the received code is